and welcome again to another tutorial. Last time we talked about the normal image classification approach. So before going to the next lecture, I want to clear some things out. If you remember, we talked about the models and we also printed the summary of the model and we saw certain layers along with the output shape parameters. Now I want to make this clear here as in how these parameters are being calculated, because this is something that is very important to keep in mind, so that because as we progress through the course there would be certain things that would come once again. So if I clear it right now, it would be much more feasible. Okay, so let's see how does this work here. So this was our original parameters as well as the layers. Now, what does this mean? So none comma 784, none basically means that none is actually the batch size. Batch size basically means that how many number of images we have here. That means it says that none basically means it can take any dimension. So none comma 784 means in the input layer. So if we talk about the input layer, we have 784 neurons. Yeah. So this basically means none comma 784. And in the next layer we have 300 neurons. So we have 300 neurons in here. Now if you remember our previous conversations about how these mappings actually happen, I said that we assign, so this goes to every other neurons, and with every neuron there is a weight associated like theta naught, theta 1, etc, etc, similarly like this and so on. Now we can take all these weights and put it in a matrix. That matrix is called as W, and this is actually nothing but our input, that is X. So if you remember our previous conversation in which our function was given by theta transpose X plus B bias, right? So we can also figure out the function here. So if I take all the weights theta naught, theta 1, theta 2 dot dot and put it in a weight matrix, something like this as a W. Yeah, so this is like here. So this is theta 1, let's say this is theta 2 and so on. If I take all the matrices in here, X value, and if I do if I take, okay, so this is my first element X1, that means this is my first image, this is my second image, something like this. So this would basically become the dimension would be here represents the number of images, and here this would be 784 columns, because as you can see that there are 784 elements here. So if I do XW plus B, this is actually equivalent of doing theta transpose X plus B. Now here you see that, okay, here theta is in front, here W, which is actually equal to theta, is in back. Why is it the case? Actually they both are the same, it's just how you arrange your parameters, whether row wise or column wise, that gives us different representation. So XW plus B. So here there are 784 neurons. So let's say there are P number of images. So P cross 784, this would be the dimension of this. Now we need to figure out the dimension of W, because W are actually the parameters. I know that then in the first layer there has to be 300 neurons. So that basically means somehow this W matrix should get multiplied by this and it should output 300 numbers. How would it do that? Well, I know that to multiply two matrix P, Q and X R, this Q and X should basically be the same. So if it is P into 74, I can make this W as 784 cross 300, because when I will multiply this, I will get P cross 300, and that's what we want, right? Because there are 300 neurons. So the number of parameters would be 784 cross 300 plus 300. Why 300 plus? Because I said earlier that with every neuron we also add a bias. So we have 300 neurons, so we add 300 in here, and this would result in 235500, which is this number. That's how we got the parameter. Similarly for this case, so here now 200 neurons are there in the next layer. So this the same case. Now you can imagine this as the input layer, this is the output layer. So P cross 300. So we have P cross 300, right? Now in the next layer we have 200 neurons. So this the W should be 300 cross 200 plus 200. And if you multiply this, you will get 60 200. That's how you can also calculate for the last layer. So I guess this actually clears out some of the confusion as in how we got the number of parameters. Now before moving forward, I want to clear out a small concept, which is overfitting and underfitting. What this basically means, in extremely simple terms, um, underfitting actually relates to the complexity of the model, meaning, let's say, as you already remember, this neural network actually represents the functions, right? So we take so many easier functions, we combine them together to make complex functions. Now imagine that we have a data set that was generated by a, let's say, polynomial function. Let's say a 4-degree polynomial, like something x4, like a times x4, b times x3 plus dot dot dot. Yeah. So this is actually the function that actually generated our data set. So we got some points. Yeah. Now, let's say we created a neural network, but in that neural network, simply just gave me the polynomial in 2 degree. Let's say as ax2 plus bx1 plus some constant c. Now that basically means, what am I trying to do? I am trying to approximate a data set that is generated by a 4-degree polynomial by a 2-degree polynomial. Now you can clearly see that I want to be able to recognize all the patterns, right? Why? Because my model is not complex enough. And when that happens, that is what called as underfitting. And when that actually happens, you can see in the plot that the validation loss, so suppose this is my validation and this is my training, and let's say this is some plot, right? Your validation loss and your training loss will both be very high. And if that happens, that when your training loss and validation loss both are very high, that basically means the model is underfitting. In that case, what you should do, you can actually increase the complexity of model by adding more layers, right? Or you can add more neurons per layer, etc. Overfitting. Now, overfitting is just the opposite. Now, let's say your data set was generated by a 2-degree polynomial, right? Let's say a times x square plus b times x1 plus c, and you try to approximate using a 10-degree polynomial. Let's say ax10 plus b x9 plus dot 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 dot. Now, the thing is, of course, this polynomial would be able to approximate this data set, but the problem is these points. Sorry, the problem is that this model will literally memorize every point of the data set, and that is a problem. Why is it a problem? Let's understand something. So let's say we are doing a regression program. Yeah, we are doing a regression program, and we had some data sets something like this. There's some points like this. Now you know that for regression we need to find a good line that sort of which is very close to all the points, right? So this is one line, and I see that yes, it's a very good, because you see that the perpendicular distance with every point is very small. So I can say that yes, it's a very good model, right? Another model that I can create is something like this. Let's say, okay, this is the first point, this is first yellow point. Oh, sorry, let me make it much more clear. So, okay, let's say this is my first. So these are my points. Okay, these white are my points. Okay. Now, if I take the red model, now you see it goes through first white point, and the second, then third, and fourth. Now you can see it is literally hitting every point. I mean, ideally, if you see that this red should be much more better than and this might go something beyond like this, much more better than blue, because it is literally hitting every point. It is literally very close to every point. But the problem is, What about some data that we haven't seen in real world practice? A real world practice model, a point might be something like here. But this red, which is an overfitted model, which is a very high degree polynomial model, it literally went somewhere else, right? Like somewhere else, because it is a very complicated function. But the blue function sort of remained there. Now, as you can see that for unknown points, for real world problems, this blue model would actually do a better job with their red model. That is why overfitting is actually a problem. So, in order to reduce the overfitting, the simple idea is that you simply reduce the complexity of the model. Maybe you should reduce the number of layers or reduce the number of neurons per layer. So, that's what the idea is. So, let's first of all import our SSL libraries. So last time we created a sequential model, but this time we will actually deal it with a functional model. So let's first of all get the data set. So housing is equals to fetch California housing. Okay, let's get the number of samples. So number of samples is actually the total number of elements in the data set. Samples your housing dot data dot shape 0. Okay, so we got that. Let's print it and see that how many number of samples we have. So we run this. Total 20,640 samples are there. So first of all, we need to split it into training and validation, like I already told you in the last lecture. So let's first of all get some indices. So np.arange, what arange does, it simply creates the samples. So if let's say n of samples is 10, it will create an array like 0, 1, 2, 3, till 9, yeah. And then we shuffle it. np.random dot shuffle. Note that this is actually a in place function, that means it will simply shuffle the indices array. Now let's first of all take the x and y. Let me make it this small. X and y. Housing dot data, and we take the indices. So here we first of all shuffled target indices. Okay, now first of all we fetch the training size. What should be the number of elements in the training? Well, we simply take the 80-20 rule. That means 80% of the elements should belong to the training, and the remaining should belongs to the validation set or your test set, whatever you are trying to create. So let's now split into x train and y train. X train, y train. Your x of training size and y of train size. Similarly, we can take x test, y test. We take x of train size and y of train size. This is one of the simpler way to actually split the data set. There are also other approaches, and we will learn as progress through the course. I'm already quite behind because I was sick, but now I will upload many videos as well, so that we can catch up the pace. Okay, so if I run the program, so we have in the training data set 16,512 elements, and the number of features are 8. Okay, now before going forward, we need to first of all standardize the data set. Now, what is standardization? In extremely simple terms, in normalization, I talked to you about we take every element, every pixel can take value from 0 to 255, but I wanted to bring it in a small range between 0 and 1 so that our gradient updates won't be much more erratic. Standardization basically means that calculate a z-score. In a regression, you can imagine that okay, we have several points. Those several points, we can calculate the mean of those several points, and then we can take a point, we can subtract it with the mean of those points, and we can divide it by the standard deviation. And what will that give me? This will actually give us like how much far it is from the mean. Every point, like how much far it is from the mean. And this is like one of the way to sort of standardize the data set. So either we can do it manually, but there are also functions for it. Right now, let's use function. Um, so it's from scale under pre-processing, I guess. Import standard scalar. Yeah, it's there. So we take the scalar and standard scalar. Okay. So then x train scaled. So we take the scalar dot fit underscore transform. So fit underscore transform means fit will first of all it will automatically calculate the mean of the points and it will automatically subtract the mean and divide by standard deviation from all the points. X underscore train, and then we will do the same for your test data set. X underscore test scaled. This is scalar dot transform. Why I didn't do fit underscore transform? Because I would use the mean of the training set to actually fit the points here, not the mean of the test set. Because why? Because the model will actually learn from the test set, sorry, from the training set. So of course, the same sort of pattern should exist in the test set. So we should use the same mean rather than the different mean. Okay, with that done, now we will create the functional API model. So in the last lecture we created the sequential model, but now we will solve the same problem using the functional API model. So let's first of all define an input layer. So tf.keras.layers.input. Now you define the shape. So earlier we used flatten and then we define input underscore shape. Either you could do that, but or you could also define the input using the input layer and you can simply give the shape. My shape is well x train scaled dot shape. So this will actually give us a shape. So this is like you can imagine this input layer as one function or yeah one function. Or I mean rather than function you can imagine this as input. Yeah. And then let's take the first hidden layer and let's create the first hidden layer. So tf.keras.layers.dense and let's say I just take 30 neurons for the first layer. Layers.dense and then I define activation function. I don't know what's wrong with my spelling today. So this is now one function, and I need to pass this input to this hidden layer, right? So you can imagine this as a function. Call this function on the input layer. Now you see how I'm doing this. I'm taking the input and passing it to this function, this whole function. So now I got the first hidden layer. Similarly, I can let's say define one more hidden layer. Let's say tf.keras.layers.dense, then activation. Again, let's say value, and then I take the hidden one. The same approach. Now I can define the output layer. That is tf.keras.layers.dense. Now since it's a regression problem, that means the output should be just one real value. So I don't have to provide any activation function because the output can take any real value. That's why. So hidden 2. Now we can define the model. So I know the input, I know the outputs, now we can define the model. So Keras.model, I can take inputs as the input layer, and I can define the outputs as the output layer. Now the same thing, you can print the model summary, print model summary, you can print the layers, model dot layers, you can get the weights. Let's also get the weights and biases, yeah, so that we can see how does this look. This is just exactly like how we did in the first get underscore weights. We can print the weights dot shape, print the biases dot shape, and let's print it. Let's see whether do we get any error. Hopefully we should not, but let's see. Okay, so this is exactly like before. Okay, I think we got an error here. Let me see what error did I get here. Where is it? Okay, 1 minute. I think I made this mistake. So we need to first of all fetch that layer. So model dot layers. So this is the list of layers. Now we need to select which layer I'm talking about, the first layer, and then we pass this here. We run it again, and voila, we got the. Okay, so this is exactly like before. Now this is like the first layer which has 8 neurons, input layer, and then the second that is the first hidden layer which has 13 neurons. Now if you remember, so what should be the dimension? So this is p cross 8. So I need to have the first matrix as 8, 30, so that I get 13 here, exactly like before. It's just here it's given 8, 30, and we need to have 30 biases, that means 30 elements, and you can multiply 8 into 30 plus 30, you will get this number. Similarly this. So good, I guess our model is ready now. Now we can actually do the training. So we need to first of all compile the model. So loss, well, we can simply take the MSE loss. So we can take the mean squared error loss, and we can take the optimizer. We have .keras.optimizers.sgd, stochastic gradient descent. So I will fit the model x train scaled, comma, we have y train. So let's train it for 30 epochs. Yeah, so let's train it for 30 epochs, and let's do prediction. So prediction would be model.predict, right? And we need to predict it on, let's say, test scale. So right now I'm not using any validation data set. You can use some validation data set, but it's actually quite simple data set, so we don't have to, do that. And also let me flatten it out. So flatten basically means the same thing, like it's like the flatten layer. It will just take the inputs and make it like 1D array out of it. And then we can also print the MSE. So if you remember how MSE is defined, I've also told it in the previous lectures. So we take, okay, let me show how it is. We take the mean. Okay, so we have to take the mean. We will take every prediction, we will subtract it from the right answer, and then we square it out, right? This is y test. Yes. Let's also plot the residual. What residual means? Residual plot basically means it says that, okay, let me show you what residual is. So residual is, okay, so we take your y test, yeah, and we subtract it from prediction. Now suppose if prediction is very close to your y test, so this residual should be 0, right? But if it is far, then the residual would be some points. So if we simply plot the residual, and if all the points or majority of the points collaborate at point 0, that basically means your function is doing good thing. If not, then if not, then we need to figure it out what went wrong, and maybe it's underfitting or overfitting, and then we need to uh, like we need to then take the appropriate action. So 0.5 alpha 0.5 basically means the size of the dots. Yeah. So let me also define a horizontal line on 0, right? Because that will show where exactly our 0 is, and then we will know how good or bad our code was. So I can define some line style. Okay, now let's define proper labels. So at x, we have predicted. On y, at t.y label, we have the residual, and we can give also the title for the plot. Let's say residual plot, and then we can show the plot. Oh, I guess we wrote quite a little bit of code. I hope it runs. Okay, so the MSA is 0.319. So without validation loss, we cannot do proper debugging because we won't know whether it's underfitting or overfitting. But now here you see the model. Okay, so like these are the residuals, and you can see that okay, if this is 0, they are very scattered around. That this model is, so this is like here. This is maybe it would be an outlier. And if you see that, okay, there are points which are very close to zeros here. So this is like one plus term. You can see that, okay, for this point, the output is okay because here you can see the 0 and this is 1. So if you see here up to 1, then these all points are very close to 0. Now these are points that actually went to 3, and it actually went to 2 and then 1. So this is actually doing a good job here because as you see that they are also close to zeros. But we might do much more better, right? We might do much more better, but for that we need to create validation loss, validation set, and then we need to plot them out. We need to figure out where it's underfitting, overfitting, or what problem went wrong and all. But we won't be doing that right now. So right now today it's all about how you create the model, how you see how many parameters are there, and etc. So this is how functional API model works. And the good thing about the functional API model is that it's not just limited to this. I mean, you can have multiple inputs and you can have multiple outputs. So that's also like a very good thing. Okay, let's create another model. So a model which has, let's say, 2 inputs and 1 output. So let's create something like this. Let's say if I take input A, let me show you how it works. So tf.keras.layers.input, and let's say this first input layer contains 5 neurons. Yeah, and I can also give the name to a particular layer. Let's say input A. Similarly, we can have another input tf.keras.layers.input shape. Let's say I have 6 neurons here, and name is input B. Let's say I take first hidden layer and tf.keras.layers.hidden, sorry, not hidden, dense, let's say 30, yeah, and we take some activation function, let's say value, and let's say I pass this to my second input, right? I don't pass it to first input, and let's say I take hidden 2, and I tf.keras.layers.dense 30 activation we take where is it, ReLU, and then hidden one, right? And we can also concatenate it. So I just want that, okay, just take the output of the hidden layer 2 and just concatenate it. Just concatenate with the input A. So you take the input A and you concatenate with the hidden layer 2, right? Yeah, okay, and along the last axis, along the channel axis, that means you just take the number of so if let's say this is output 30, this is 5, so this would probably be 35, none comma 35. So along the last axis I'm simply concatenating it, and then you get the output of the model, length 1, you know, and you can also provide some name, let's say output, yeah, and you pass your concat layer in there, and then you define your final model. So tf.keras.model inputs. So you give, let's say, your input A and then your input B, and then you define your outputs as your output layer. Voila! And then you can print the model dot summary to see how it went down. You can then compile your function. Let's say model.compile. So loss is equals to your MSE, and then you can also define your optimizer, like tf.keras.optimizers.sgd. Yes, and then you can do model.fit. Now model.fit, how do we do it? Well, we have two inputs, right? So we need to give two inputs. Let's say I give x train and I also give y. Sorry, I give x train and you can give x test. Or you can also give x train again, two times. And then you define the output. Well, there is just one output, that's a y train. If had it been two outputs, then we would give it the same format as this. And then you can define epochs, let's say 30, and so on. Right? Let's try to, let me comment this out. Okay. Okay, so this we have none comma 6, 35, and so this is our second dense layer, and then we merged it out none comma 35, and then we got none comma 1. So it's the input 0 of layer function 1 is income. Okay. So this would be 8, because if you remember, we had 8 number of features, right? So that's why. Because this 8 should actually it should be equal to this shape, right? So that's why. Yeah, now you see your model is compiling, and then it's NaN basically means sometimes NaN simply represents the extreme cases, either extreme small or extreme high. Yeah? But I mean, like, training wasn't our objective. I just wanted to show you how it gives much more flexibility to you to use the functional API model, and this model we will be using a lot. So I guess for today that was it. I hope you understood the concept of functional API model, and I'll see you in the next lecture. Radhe Radhe.